decides this language. In other words, for every element, like of this form, belonging to this language, the Turing machine that we construct, the algorithm, same thing, will accept it. And for all other strings, in other words, not belonging to this, that algorithm, that Turing machine, would reject this. And from that, you have an answer to your question. You have a yes/no answer to your question, because if for a particular regular expression, a particular string, if this ordered pair does belong to the language, well, then you know that this. The answer is yes. This regular expression does generate this string. And if the pair you're talking about, some arbitrary regular expression and some arbitrary string, if that arbitrary regular expression does not generate that arbitrary string, then that pair will not belong to this language. And so therefore you have the answer no. So a reject. So the machine, the Turing machine you have designed, would reject. And hence, this machine always either accepts or rejects, therefore it decides. So you have a decider, a Turing machine that never loops, right? It always halts. So you have a decider, and therefore you can you get an answer to your question, yes or no. Does a particular regular expression R generate a string W? Right? That's how you solve your computational problem, by converting it into a kind of belonging to a language type problem, and then constructing a Turing machine that decides that language. Okay, so I have summarized it after all. Okay, that should be fairly clear from previous board, and you've got it again. All right, so let's here we have from here onwards. We have our standard format for describing standard format description of a Turing machine. And in this case, we're trying to find an algorithm, Turing machine, same thing, that decides the language, this language. Okay, so it's a proof by construction. So if we can construct the Turing machine that does decide that language, then we have an answer to our computational problem. Does R generate W? Okay, so the proof takes the form of, it's a proof by construction. We have to construct the Turing machine that decides the language. So how to do that? Okay, and as usual, so we construct this Turing machine, this algorithm, in other words, and in standard format. So as usual, we start with a description of the input string. Well, it's this. The angular brackets, remember, we've done this quite a few times now. So that the angular brackets imply a representation, an encoding of the information about the regular expression and the string. Okay, so that's your input string, goes into the Turing machine. Turing machine always has an input string, where R here in the sorted pair, R is some arbitrary regular expression. And we've talked about regular expressions at length in chapter 1. Okay, and W is just an arbitrary string. All right. Now, as usual, any proof typically will have at least one central idea, some core idea that is the heart of the proof. Now, in this case, the basic idea is to convert your regular expression into an NFA, and we can save. And by doing that, we can save ourselves some work, right? because we've already discussed NFAs. That was on the previous board. So we can then use previous theorems, save ourselves work. After this conversion, after we convert the regular expression into an NFA, now we know how to do that. We talked about that in chapter 1. In fact, go to theorem 1.54. It's on page 66 in your text. Refresh yourselves, where this theorem shows how to convert a regular expression into an NFA. Okay, so once the Turing machine has checked the format of this, that it's legal, that it's okay, there are no errors that way, because if there are errors, it immediately rejects. Okay, so if this input is fine, then the Turing machine will extract all the information about the regular expression, and then as a component of itself, this Turing machine, it will have a conversion component, if you like, based on this technique, which will convert the regular expression into an NFA. And then once it's got an NFA, it'll have another component, part of this larger, if you like, Turing machine, and it will do the theorem that's appropriate to showing that an NFA, the language of the equivalent language of an NFA is decidable. We did that. Previous board, right? Okay, so the core idea is convert your regular expression into an NFA. Okay, and call that NFA, that machine, call it A. Right. All right. Now, so your A now is a machine. It's not a regular expression or grammar, or it's a machine. So we've converted R into A. A is a machine, an NFA. Okay. And so now, as usual, the standard format description of an algorithm. I usually break it into stages, and we number the stages. Oops, I forgot the final double quote. Right. That's part of the standard format description. Opening double quotes and ending double quotes. Alright, so the stages are numbered. Now stage 2, what do you do then? Well, you've got this NFA now, you've got the string, that doesn't change. Right? And so as a part of this, I'll call it Turing machine P. Okay, yeah, following Turing machine P. And it is to decide this language, this language here, regular expression, AREX, of this form. Alright, so Turing machine P will have as a component Turing machine N. Go back to previous board, a couple of sessions back, when we were talking about whether an NFA will accept a random NFA will accept a random string. Okay. So N is the Turing machine that decides the corresponding language of this form. Okay. So its input, the input to N now, go back a session or so, will be of this form. Right. So it's not to RW, it's now AW. So this is the input that goes to this Turing machine. The input of this Turing machine N expects the first thing here in the ordered pair of your string, string members of the equivalent of this. What was, I think it was A NFA, right? So it expects this here to be an NFA, right? So you input this string and see